Welcome to the final tutorial of this course. Today we will solve few problems based on reaction thermodynamics and thermodynamic property relations. So, let us start it. Methane is burned with dry air. The volumetric analysis of product on a dry basis is 5.2% of CO2 is coming out, 0.33% of CO is coming out, 11.24 oxygen and 83.23% nitrogen. We have to determine the air fuel ratio and the percentage of theoretical air used. So, what is happening here? Methane is being burned with air. And this air is dry. Okay. Now, the product stream contains CO2, CO, oxygen and nitrogen. So, first we have to determine the air fuel ratio. We take a basis of 100 kilomole of dry product. Basis is 100 kilomole. So, on this basis we can directly take the composition of CO2, CO, O2 and nitrogen in the product stream. Before writing combustion equation, first we assume that x kilomole of methane is being burned, okay, because it is not given in the question. So, x kilomole of methane is being burned with a kilomole of air, since 1 kilomole of air contains 1 kilomole of oxygen plus 3.76 kilomole of nitrogen, and the product stream will have 5.2 kilomole of CO2 and 0.33 kilomole of carbon monoxide plus 11.24 kilomole of oxygen plus 83.23 kilomole of nitrogen, and oxygen and hydrogen will react and form water. So, certain kilomole of water will produce in the product stream. From the mass balance we can obtain the unknown variables. Okay. So, after making mass balance for nitrogen, we get 3.76 A equal to 83.23. So, from here we get A equal to 22.14. Similarly, mass balance for carbon, we get X equal to 5.2 plus 0.33. So, that gives X equal to 5.53. Okay. And similarly for hydrogen, 4x equal to 2b, that means b equal to 11.06 using x equal to 5.53. Okay. Now, after substituting all these values in the combustion equation, we get 5.53 CH4 plus 22.14 kilomole of air, that is 3.76 nitrogen, and then product streams contain 5.2 kilomole CO2, 0.33 carbon monoxide and plus 11.24 oxygen plus 83.23 nitrogen and 11.06 water. Okay. So, now for 1 kilomole of fuel combustion, equation can be written as CH4 plus O2 plus 3.76 N2 gives 0.94 CO2 plus 0.06 of carbon monoxide plus 2.03 of oxygen plus 15.05 nitrogen plus 2H2O. Okay. Since we have been asked to calculate air fuel ratio, okay, so in the first part we have to calculate air fuel ratio, which is equal to mass of air divided by mass of fuel. Okay. So what is the mass of air? So stoichiometric coefficient of this reaction, if you see, so stoichiometric coefficient is 4 for air multiplied by total kilomole of air, so which is 4.76 kilomoles, and since 1 kilomole of air contain 29 kg, okay, divided by mass of the fuel, that is mass of carbon plus mass of the hydrogen. So mass of carbon, since here stoichiometric coefficient is 1, so 1 kilomole times 12 kg per kilomole plus 2 kilomole times 2 kg upon kilomole. Okay. So from here we get air fuel ratio equal to 34.5 kg of air divided by kg of fuel. Okay. Now in the second part we have to determine theoretical air. So for that we need to know the theoretical amount of air, and that can be obtained from theoretical combustion equation. Okay. So in the second part, if you write combustion equation for theoretical air, that means complete combustion will take place, 3.76 nitrogen. Since complete combustion will take place, so the product stream will contain CO2, H2O and nitrogen. Okay. So CO2 plus 2H2O plus 3.76 A theoretical into nitrogen. Okay. From the mass balance of oxygen, we get A theoretical equal to 1 plus 1, which is equal to 2. Okay. Now the percentage theoretical air is equal to mass of air is equal to actual mass of air divided by theoretical mass of air. Okay. This is equal to actual moles of air divided by theoretical moles that we have used in the complete combustion. So 4 into, now we know actual moles of air, which are 4 into 4.76 kilomole divided by 2 times 4 into 76 kilomole. Okay. This comes from theoretical combustion. Okay. Into 100. Now to get a percentage, so this gives 200% of theoretical air. Now moving to the next question. Methane is burned completely with the stoichiometric amount of air during a steady flow combustion process. If both the reactants and products are maintained at 25 degrees centigrade and 1 atm, and the water in the products exists in the liquid form, determine the heat transfer from the combustion chamber during this process. And what would your answer be if combustion were achieved with 100% excess air? Okay. Since fuel is burned completely, so the product will contain only H2O, CO2 and nitrogen. Okay. So, considering one kilomole of fuel, okay, if you write combustion equation, then it will be like CH4 plus A theoretical air will give CO2 plus water plus 3.76 A theoretical N2. Okay. From mass balance, A theoretical equal to 2. Okay. After substituting, we get CH4 plus 2 times O2 plus 3.76 nitrogen gives CO2 plus 2H2O plus 5.64 kilomole of nitrogen. Okay. But we have to determine amount of heat coming out of the combustion chamber. So, what is happening in the combustion chamber? Methane is being burned with air. Okay. It is entering into the combustion chamber at 25 degree centigrade and leaving it at 25 degree centigrade as well. Okay. And the combustion is being done at 1 atm. So, we have to determine the amount of heat coming out of this combustion chamber. Since temperature is constant, so it will lose its energy to the surrounding. So, that heat can be obtained by energy balance on this combustion chamber. So, from the energy balance, what we get, E in minus E out equal to delta E of this system. Okay. And here we assume that air behaves as an ideal gas. Okay. And we know that delta E system is nothing but delta of the internal energy plus delta of kinetic energy plus delta of potential energy. And we also assume that change in kinetic energy is 0, potential energy is 0, since temperature is constant. So, this delta U will also be 0. That means, energy in will be equal to energy out. Since there is no shaft work, so this is the W dot will be 0. So, the total heat coming into the chamber is the heat of the reactant. Okay. So, the heat of reactant is nothing but the number of moles of reactant times enthalpy of formation of reactant at that reference temperature plus enthalpy at working temperature minus enthalpy at reference temperature. Okay. Will be equal to number of moles of product stream times enthalpy of formation plus enthalpy at working temperature. So, that is H minus H naught of the product. Since working temperature and reference temperature are same in this case. Okay. T equal to T naught, which is 25 degrees centigrade. Okay. So, one more thing is missing here, Q is coming out. Okay. So, Q out will be there. So, after solving it and rearranging, we get Q out equal to number of moles of product times enthalpy of formation of product minus number of moles of reactant times enthalpy of formation of reactant, because these terms will be 0 since working temperature and reference temperatures are same. So, we need to find out Q out. For that, heat of formation data for all the substances are given here. Okay. So, utilizing these heat of formation data, we will calculate Q out. Okay. So, after plugging all the heat of formation data, which is Q out equal to 1 into 393,520. These are the enthalpy of product streams, 2 times minus 285,830 plus 0 minus enthalpy of the reactant, 1 into 74,850 plus, because naturally occurring gases will have 0 heat of formation like nitrogen and oxygen. So, after solving it, Q out will be 890 kilojoule per kilomole of CH4. Okay. So, this much of heat will come out of the combustion chamber. It has also been asked that if we use 100% excess air, then what will happen to this energy. So, if combustion is achieved with 100% excess air, the answer would be the same, since it would enter and leave at 25 degrees and absorb no energy. So, answer remains same. So, moving to the next question, determine the change in enthalpy of air in kilojoule per kg as it undergoes a change of state from 100 kilopascal and 20 degree centigrade to 600 kilopascal and 300 degree centigrade, using the equation of state P V minus A equal to R T, where A value is given 0.01 meter cube per kg, and compare the results with the ideal gas equation of state. Since equation of state is given, which is equal to P V minus A equal to R T. So, after solving it for V, we get V equal to R T by P plus A. Okay. First we get derivative of volume with respect to T, keeping pressure constant, and from here we get R upon P. Now, we will utilize this expression to get enthalpy, since we know dH, change in enthalpy, is equal to Cp dt plus V minus T times del V upon del T at constant P dP. So, this is the general expression for any equation of state. So, substituting this value here, we get dH equal to Cp dt plus volume is RT by P. Okay. So, RT by P plus A minus RT by P. Okay. So, this gets cancelled out, and what we get from here is dH equal to Cp dt plus A times dP. After integrating it, we get H2 minus H1 equal to Cp T2 minus T1 plus A times P2 minus P1. Okay. Cp can be obtained from the table A to B, okay, and this can be obtained at average temperature T1 plus T2 by 2. So, since temperature is changing, okay, it is not constant. So, corresponding Cp is equal to 1.018 kilojoule per kg Kelvin, okay. So, after substituting all these values in this expression, we get H2 minus H1 equal to Cp dt, that means 1.018 kilojoule per kg Kelvin times delta T, which is 300 minus 20 Kelvin, plus value of A is given, which is 0.01 meter cube per kg times delta P is 600 minus 100 kilo Pascal. So, after solving it, we get 290 kilojoule per kg, okay. So, this much of enthalpy will change. We have to compare this result with ideal gas equation of state. Since we know enthalpy of ideal gas is a function of temperature only, okay, and from there we get dH equal to Cp dt, okay. After integrating, we get H2 minus H1 will be equal to Cp T2 minus T1. So, we know Cp value 1.018 kilojoule per kg times 300 minus 20 Kelvin. So, this gives 285 kilojoule per kg. Now, you can see the difference. Here change in enthalpy is less than that of the previous case, okay. Now, moving to the next question. Derive an expression for specific heat difference of a substance whose equation of state is this. So, it is given that equation of state is PV minus A equal to RT, and now we have to determine Cp minus Cv value, okay. Since we know Cp minus Cv is equal to beta square Tv upon kappa, where beta is volumetric expansion coefficient, okay, kappa is isothermal compressibility factor. So, if we see beta is equal to 1 by V del V upon del T at constant pressure, whereas kappa equal to minus 1 by V del V upon del P at constant temperature, right. So, if we insert it here, we get Cp minus Cv equal to minus T del V upon del T at constant pressure square, then del P upon del V at constant T. Since equation of state is given, we need to find del V by del T and del P by del V from this equation of state. So, solving this equation of state for V, which is specific volume, V will be equal to RT upon P plus A, okay. Taking derivative with respect to P, del V upon del P at constant T will give us minus RT upon P square, okay, but we need del P upon del V, right. So, after solving it, we get del P upon del V at constant T equal to minus P square upon RT, right, and taking derivative with respect to T of that equation of state at constant pressure will give us R upon P. So, substituting all these values, we get Cp minus Cv minus T times R by P square into minus P square upon RT. So, this gives R. Okay. So, Cp minus Cv will be equal to R. So, with this we have completed this course. Hope you have enjoyed this course. Thank you.